Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Thanks for having me back.
Oh, absolutely. So to start us off, I want you to imagine standing next to a massive spinning grinding wheel on a factory floor.
Oh, man. Yeah, that's a terrifying thought if you know what's going on inside.
Exactly, because you can't see it.
Right.
You can't feel it. But buried deep inside that solid block of abrasive material is a microscopic thermal crack.
Right.
And in a fraction of a second, the immense centrifugal force of that machine is going to tear that wheel apart. It turns it into like lethal shrapnel flying at hundreds of miles an hour.
Yeah, it's a nightmare scenario.
It really is. So today, we're finding out how engineers actually stop that from happening, along with, 100 other invisible disasters waiting to strike.
Yeah, consider this an absolute masterclass in plant mechanical engineering.
Exactly. So whether you are currently studying for a brutal thermodynamics exam, or maybe you're prepping for a massive plant design meeting, or, hey, maybe you are standing on a catwalk right now, just trying to figure out why your system is failing.
Right. Well, this deep dive is your ultimate shortcut to being well-informed.
You got it. You are tuned into Mechanical Engineering Made Simple, and we are about to pull back the curtain on how industrial plants actually breathe, move, and survive.
It is a massive undertaking, but we are going to build this understanding from the ground up.
Yeah.
We're basically going to track the lifeblood of an industrial plant from start to finish today.
Okay, so what's the roadmap look like?
Well, our syllabus for today begins with the fundamental thermodynamics of energy and fuels. Because, we have to understand the true nature of what's driving the system.
Right.
From there, we'll move to the prime movers, so the pumps, fans, and compressors.
The heavy hitters.
Exactly. Then we'll explore heat exchange, touch on the gritty, dangerous realities of machining the hardware on the factory floor, and finally bring it all together with system-wide energy auditing.
I mean, I love that roadmap, but I want to stop you right at the beginning.
Oh, sure.
Because before we can even talk about, moving fluids around or burning gaseous fuels, we really have to understand the energy itself.
Yeah, that's critical.
And I feel like this is where so many people, myself included, honestly, get tripped up right out of the gate.
How so?
Well, we were taught the first law of thermodynamics since, high school physics?
Right, energy cannot be created or destroyed.
Exactly. It's an absolute law. But if that's true, if energy is always conserved, why do I walk into an industrial plant and see huge utility costs completely wasted?
Yeah, that's the big question.
Right. Like if we aren't destroying energy, what are we actually losing?
That paradox is, it's the ultimate misconception in engineering. It plagues even veteran designers, honestly. Oh, absolutely. Engineers often obsess over first law efficiency. They balance the energy equation perfectly on paper, tracking every single joule of heat entering and leaving the system.
Right. They make the math work.
Exactly. They say, look, energy is conserved, the math works, and then they wonder why the physical system performs terribly in the real world.
So what are they missing?
What they're missing is a completely different concept called exergy.
Exergy. Okay.
Energy is always conserved, yes, but available work, like the usefulness of that energy, is continuously and permanently destroyed.
Wow.
So exergy is defined as the maximum useful work that is possible relative to the environment.
Okay, let's unpack this concept of relative to the environment. What does the environment have to do with the energy inside my closed pipe?
Well, we refer to the environment as the dead state.
The dead state. Sounds ominous.
It kind of is, thermodynamically speaking. Imagine your entire system eventually coming into complete thermal, mechanical, and chemical equilibrium with its surroundings.
Okay, so like the atmospheric temperature, the ambient pressure of the room you're standing in.
Exactly. Once a fluid or a piece of machinery reaches that dead state, you cannot extract any more useful work out of it.
Oh, I see.
Like, think about a cup of coffee at room temperature. It has thermal energy, yes, but it has no exergy. It has no potential to do work relative to the room.
Right, because already balanced out.
Exactly. Exergy measures exactly how much potential you have before you hit that dead state.
Okay, wait. I think I have a way to visualize this. Tell me if this works.
Let's hear it.
So, focusing only on the first law is like tracking every penny in your budget, but ignoring the fact that inflation is eating your purchasing power.
Oh, that's good.
Right. Like, I might have the exact same number of pennies in my bank account over a 10-year span, so the energy is conserved. But what I can actually buy with those pennies has drastically decreased.
Nah.
So exergy is the actual purchasing power of the energy.
That is a phenomenal analogy, yeah. You still have the same number of pennies, but the purchasing power has been irrevocably destroyed. And this leads us to a crucial method in modern thermal design, which is entropy generation minimization, or EGM for short.
EGM.
Right. Exergy analysis by itself is brilliant, but it rests entirely on pure thermodynamics. It assumes somewhat idealized conditions.
Which don't exist in a real plant.
Exactly. So EGM takes a massive step further. It combines fluid mechanics, heat transfer, and thermodynamics to model the realistic, messy systems we actually build.
Because a real system is never going to be that frictionless, perfectly insulated theoretical model we see in textbooks.
Not even close.
There are always going to be losses.
Yeah, EGM accepts a harsh reality, which is that the system will always operate irreversibly.
Right.
There will always be friction scraping the fluids in the pipes. There will always be a temperature drop required to push heat across a metal heat exchanger wall. You just cannot stop entropy from being generated.
So what's the goal then, if you can't stop it?
The goal of EGM is to model the actual physical characteristics of the system, like the pipe dimensions, the thermal conductivity of the metals, the constraints of the factory floor, and get the actual entropy generated as close to the theoretical minimum as physically possible.
I am assuming there is a mathematical foundation for this that ties exergy and entropy together.
There is, yeah. And it is a beautiful piece of physics called the Gauss-Stodler theorem.
Okay, Gauss-Stodler.
Right. When we talk about the available work transfer rate from an open system, we rely on this theorem.
Can you break down the math for us in a way that, makes sense spoken out loud?
Definitely. It states that EW equals the weight of useful power delivered in the limit of reversible operation minus T0 multiplied by the rate of entropy generation,
Okay.
with T0 being the ambient absolute temperature.
Let me make sure I'm grasping the implication of that math. It is proving a direct proportionality, right?
Yes.
Every bit of entropy you generate directly subtracts from your useful power.
Every single bit. It is a direct penalty. Every time a fluid tumbles over a rough pipe weld, every time a bearing creates a microdegree of friction, entropy is generated and exergy is destroyed.
That sounds incredibly theoretical, though.
It does, but it has massive real-world applications that save huge utility costs.
Well, the application that absolutely blew my mind when I was reviewing the source material for this deep dive was the cryogenic supports.
Oh, yes.
Can we walk through that? Because it sounds like science fiction to me.
It really is a brilliant application of EGM. So in low-temperature refrigeration, like let's say the helium liquefier, you have mechanical supports holding the internal equipment.
Right.
These heavy metal supports connect the cryogenic cold end, which might be near absolute zero, to the room temperature outside world.
Okay, I see where this is going.
Because they are solid metal, heat inevitably leaks down these supports from the hot room down to the cold end.
And as that heat travels down the temperature gradient, it generates entropy. It is destroying our purchasing power, our exergy. My initial instinct, just looking at it from a pure first law perspective, would be to just wrap the support in the thickest, best insulation possible. Or, I don't know, make the support out of a less conductive material.
Which is exactly what engineers tried to do for decades.
Right.
But you still need structural integrity, so you can't just use flimsy plastic, and no insulation is perfect.
So what's the EGM solution?
EGM reveals an active solution called the optimal variable heat leak principle. Instead of just letting the heat conduct all the way down the solid support and dealing with it at the bottom, you take an intermediate stream of cold helium gas, which is already flowing in the system, and you route it to flow in counterflow along the length of the conduction path of the support.
Wait, I am struggling to picture this.
Yeah.
You are actively pumping cold gas over the structural support itself.
Yes, exactly.
Isn't that wasting your precious cooling capacity on a piece of metal instead of your product?
I know, it seems totally counterintuitive until you look at the entropy math. The helium gas intercepts the heat leak incrementally along the way. Because the support's thermal conductivity changes wildly with temperature, EGM allows you to calculate the exact optimal flow rate of that cold helium to minimize the total entropy generation.
Oh, wow.
You are still going to generate some entropy, remember, irreversible. But by actively intercepting the heat at intermediate temperatures rather than letting it all dump into the absolute coldest part of the system, you save massive amounts of compressor power.
That is incredible.
And you get as close to the theoretical minimum entropy generation as possible.
We are accepting the loss, but we are managing exactly how and where we take it to preserve the maximum amount of useful work.
That's a great way to summarize it.
But listen, we've got this incredible mathematical framework for energy loss. But that framework is completely useless if we don't have energy entering the system in the first place.
True.
Where is the chemical energy actually coming from to power these industrial heaters and boilers? Let's talk about the lifeline of the plant, which is gaseous fuels.
Good transition. When we talk about gaseous fuels in an industrial context, we are primarily dealing with fossil fuels, but there are distinct categories that operators really need to keep straight.
Why is that?
Because the physical properties dictate entirely different safety protocols. The big distinction is between natural gas and liquefied petroleum gases, or LPG.
Let's break those down.
Natural gas is primarily methane and ethane. It is lighter than air, usually distributed via vast pipeline networks at high pressures, or transported cryogenically as a liquid over the ocean.
And LPG.
LPG is primarily propane and butane. It is a byproduct of natural gas processing and petroleum refining. And crucially, it is heavier than air.
I want to pause on that because I feel like the safety implications there are massive.
Oh, they are?
If I have a natural gas leak in a building, the methane is lighter than air, so it floats up to the ceiling, right?
Right.
But if I have a propane leak,
The propane sinks. It behaves almost like a liquid in the air.
wow.
It will flow down stairwells, it'll pool in basements, and fill up underground maintenance trenches.
That sounds like a disaster waiting to happen.
It really is. A worker could strike a spark in a trench thinking it is clear and ignite a massive, invisible pool of propane. That is why propane storage facilities require completely different ventilation strategies than natural gas plants.
Speaking of the gas itself, I always hear the terms sweet and sour gas out in the field. Are they actually tasting it? Like, what is the real difference there?
Well, the terminology is historical, but it is entirely about the sulfur content.
Okay.
A raw gas from a well is classified as sour if it contains a significant amount of sulfur compounds, particularly hydrogen sulfide.
And I'm guessing hydrogen sulfide is bad.
It is an absolute nightmare. It is highly toxic, literally lethal at low parts per million, and in the presence of moisture, it forms sulfuric acid.
Yikes.
Yeah, which will eat through standard steel pipelines in a matter of months.
So sweet gas is just gas that has been scrubbed of all that.
Correct. Sweet gas has had those corrosive sulfur compounds removed at a processing plant. Now, we do intentionally add a tiny bit of sulfur back in before it reaches consumers, a chemical called a mercaptan odorant.
Ah, that's the smell.
Right, that gives gas its distinct rotten egg smell so that people can detect a leak. But the amount is so minute, it has absolutely zero effect on the combustion performance or the metallurgical integrity of the pipes.
Let's talk about those leaks, because understanding how these gases burn is critical. There is a concept called flammability limits that I think is vastly misunderstood.
Definitely.
If you watch a Hollywood movie, any spark near a gas leak immediately causes a massive fireball. But that isn't the physical reality, is it?
Not at all. Combustion requires a very specific ratio of fuel and oxygen. We measure the boundaries of this ratio with the lower explosive limit, the LEL, and the upper explosive limit, the UEL.
Give us an example.
Let's take natural gas. Its lower flammability limit is about 4.3%. That means if a sealed room has a mixture of gas and air, and the gas is only 3% of the total volume, you could throw a flare into the room and the ambient mixture simply will not burn. Yeah, it is too lean. The fuel molecules are too far apart to sustain a chain reaction.
So if natural gas is 4.3% LEL, that means anything leaner than roughly 22 parts air to 1 part gas won't ignite.
Exactly. And on the flip side, the upper explosive limit for natural gas is around 15%.
Wait, so if the room is 20% gas, it won't burn either?
It will not explode. It is too rich to burn.
That is wild.
There simply isn't enough oxygen available between the methane molecules to sustain the chemical reaction. Now, obviously, at the edges of the leak where the 20% gas meets the fresh air of the hallway, it will burn, but the bulk volume is inert.
Okay, I see.
It is only in that critical window between the 4.3% LEL and the 15% UEL that you have a continuous self-sustained explosion risk.
That makes total sense, but it highlights how precise gas math needs to be. Now, here is a massive pain point I see all the time in the industry.
What's that?
A total misconception that causes huge errors when young engineers are calculating gas flow. mixing up specific gravity and gas gravity.
Oh, yeah. It is a classic disastrous error. An engineer hears the word gravity, and their brain automatically defaults to specific gravity, which is the density of a substance relative to the density of liquid water.
Right, because water has a specific gravity of 1.0.
Exactly. But when we are dealing with gaseous fuels, water is entirely irrelevant. We use gas gravity.
And what's the baseline for that?
Gas gravity is the ratio of the actual gas density relative to the density of dry air at standard temperature and pressure.
So dry air is the baseline of 1.0 for gas gravity.
Precisely. Natural gas typically has a gas gravity between 0.58 and 0.64. It is roughly 60% the weight of air.
Yeah.
Propane has a gas gravity of over 1.5, making it 50% heavier than air. If you use the specific gravity of water when trying to size an orifice plate or calculate the pressure drop of a pipeline for methane, your flow calculations will be off by orders of magnitude.
You'd completely ruin the system design.
Without a doubt.
Which perfectly sets up one of the most elegant problem-solving metrics in the entire thermal engineering industry, the Wabi Index.
The Wabi Index, or Wabi number, is an absolute lifesaver for plant operators. It is a mathematical formulation defined as the gross heating value of the gas, divided by the square root of its gas gravity.
Okay, I have to stop you there.
Sure.
Why in the world do we care about dividing a heating value by the square root of its gravity? What does that abstract number actually tell a plant operator?
It tells them if their plant is going to shut down today.
Okay, he's got my attention.
To understand why, you have to look at the physics of a burner nozzle. The flow of gas through a fixed orifice is inversely proportional to the square root of its gravity.
Moody.
A heavier gas flows slower through the same hole. The Wabi Index essentially combines the energy density of the gas with its physical flow characteristics through an orifice. It is the ultimate indicator of heat input.
Let's give the listener a real-world scenario.
Okay.
Let's say I'm running a massive industrial ceramics kiln. It relies on a steady flow of natural gas from the utility pipeline. Suddenly, there is a winter freeze, a natural gas curtailment, and the utility calls me and says, "We are cutting your supply to zero to save the residential heating grid."
It happens all the time.
I have massive tanks of liquid propane out back for exactly this scenario.
Okay.
But you just told me propane is vastly heavier and has a completely different heating value than methane.
Right, and if you just pipe raw propane gas into a burner that was physically machined for natural gas, it would be a disaster.
Because of the weight.
The heavier propane would flow slower, yes, but it contains so much more energy per cubic foot that the heat input would completely overwhelm the burner, create massive soot, and potentially melt the furnace internals.
So how do I use my backup fuel without ripping out all the burners and replacing the nozzles?
By using the Wabi Index, you take that raw propane and you mechanically mix it with ambient air before it reaches the burner.
Just normal air.
Yep. By diluting it with air, you lower the mixture's overall heating value and you alter its gas gravity.
Oh, I see.
The magic of the Wabi Index is this. If you create a propane-air mixture that has the exact same Wabi Index number as the natural gas you were previously using, your existing burner system will pass the exact same amount of heat energy with the exact same flame characteristics without a single mechanical modification to the nozzle.
That is just brilliant. It's basically the ultimate plug-and-play metric.
Exactly.
It's like matching the voltage and amperage on a universal laptop charger.
Yeah.
If the Wabi Index matches, the furnace physically doesn't even know the fuel changed.
The flow dynamics and the energy density balance each other out perfectly. It is a triumph of fluid dynamics.
Speaking of fluid dynamics, we have our gaseous fuel, we've burned it, we have thermal energy. Now, we need to actually move our working fluids around the miles of piping in the plant.
Yes, time to move things.
It's time to talk about the unsung heroes of the industrial world, rotating fluid machines, the prime movers, the pumps, fans, and compressors.
The iron heart of the facility. And to start, we really need to group pumps and fans together in our minds because they operate on the exact same fundamental physics.
Which feels wild to say out loud, right?
I know.
If I am looking at a massive cast iron centrifugal water pump, and then I look at a flimsy sheet metal ventilation fan on the roof, They don't look or sound anything alike.
They look different because of the density of the fluids, but mathematically they are identical.
Really?
Yeah, they are both dealing with fluids that are essentially incompressible in this specific context. Yes, air is a gas, but if a fan is only creating a pressure rise of less than, say, 5,000 pascals, the air doesn't compress enough to change its density in a meaningful way.
So it acts as a liquid.
It behaves dynamically just like liquid water. Both machines use the exact same principle of fluid acceleration to add energy to the system.
And the governing mass here is the Euler equation. Walk me through what is physically happening inside that metal casing.
Let's follow a single particle of water. It enters the center hole of the pump, which we call the eye of the impeller.
Okay, the eye.
Right, it's just sitting there at low pressure. Suddenly, the spinning metal blades of the impeller catch it. The rotation physically forces that water particle to travel outward along the curve of the blade.
Getting flung out.
Exactly.
Yeah.
Centrifugal force accelerates it massively. By the time that water particle leaves the outer edge of the impeller, it is traveling at an incredibly high velocity.
But high velocity isn't really what we want.
Right.
I don't want water shooting out of a pipe like a pressure washer. I want pressure to push that water up to the 10th floor of the plant.
Exactly right. Velocity is just kinetic energy. We need pressure energy, which we call head.
Okay.
So the fast-moving fluid exits the impeller and immediately enters a specially shaped outer casing. In a pump, it is called a volute. In a fan, it is called a scroll.
The casing is shaped like a snail shell. Why is that specific shape so important?
Because the casing actually acts like a fluid brake. As the fluid travels around the snail shell shape, the cross-sectional area of the casing gradually increases. It gets wider.
And so it slows down.
Right. Because the same amount of fluid is now entering a larger space, it is forced to slow down. And according to Bernoulli's principle, as the velocity of a fluid decreases, its pressure must increase to conserve the energy.
That makes perfect sense.
That physical deceleration in the volute is how both a pump and a fan build head pressure.
Okay, if the physics are identical, how does a plant designer know what shape the impeller needs to be? Like, if I have a system that needs massive flow but low pressure versus a system that needs tiny flow but massive pressure, how do you compare them?
You use a non-dimensional matching tool called specific speed.
Specific speed.
Yes. This is the ultimate guidepost for selecting the geometry of a rotating fluid machine.
And there's an equation for this, obviously.
There is. The mathematical equation is ns equals n times the square root of q divided by h to the power of 0.75.
Let me make sure I've got the variables right. N is the rotational speed in RPM, Q is the volumetric flow rate, and H is the developed head pressure.
Correct. Specific speed is a shape factor. By crunching those system numbers, you get a numerical value that immediately dictates the physical profile of the machine you need to buy.
Okay, give me an example.
A very low specific speed means you need high head pressure but low flow. That math points you to a large diameter, very narrow centrifugal impeller.
Oh, I see.
It spins the fluid out very far to build pressure, but the narrow channels don't allow much volume.
And what if the specific speed number is incredibly high?
A high number means you need massive flow but very low pressure. The math tells you to abandon the centrifugal design entirely and points you toward an axial flow machine, like a boat propeller.
Like a big fan pushing straight through.
Exactly. It doesn't fling the fluid outward, it pushes it straight through along the axis of the shaft. Specific speed takes all the guesswork out of aerodynamic and hydrodynamic matching.
That makes the selection process sound foolproof. But here is a massive pain point I want to address.
Okay, let's hear it.
Let's say the designer uses specific speed, they pick the perfect pump, and they install it. But 6 months later, the plant system demand changes, and they only need half the flow rate. The most common misconception, the biggest sin in plant operation, is thinking you can just take that pump and throttle it down with a valve to fit the new system.
It is tragic how often this happens. Let's trace the energy path here.
Okay.
The plant is caring for electrical exergy to spin the motor. The motor spins the impeller, which accelerates the fluid, which then decelerates in the volute to convert that kinetic energy into precious pressure head.
Right. The plant spent good money to build that pressure.
And then the operator installs a throttling valve right after the pump discharge and cranks it halfway closed.
By closing that valve, you are intentionally introducing a massive friction restriction into the pipe. The fluid has to squeeze through a tiny gap.
Exactly.
So you are literally turning your expensive hard-won pressure head back into useless heat via friction across the valve.
You are boiling the purchasing power of your energy. It is an incredible waste of exergy. The power wasted in that throttling process is converted directly into heat in the fluid.
That's awful.
You are basically paying the utility company huge sums of money for the privilege of heating up your cooling water.
What is the modern correct solution? If I need less water, how do I get it without a valve?
You use a variable frequency drive or a VFD.
A VFD.
Right. Instead of fighting the full power of the pump with a mechanical valve, a VFD alters the electrical frequency being sent to the motor, physically slowing the pump's rotational speed down. You simply produce less pressure and less flow to begin with.
And the energy savings are exponential, aren't they?
Massive. Using the pump affinity laws, we know that the power consumed by a pump varies with the cube of the rotational speed.
The cube.
The cube. If you use a VFD to slow a pump down to just half speed, it requires only 1/8 of the electrical power. You can save absolute fortunes a year in electricity on a single large process pump just by throwing away the throttle valve and letting the electrical drive dictate the flow.
Let's talk about the nightmare scenario for these pumps. The acronym that makes veteran plant engineers break out in a cold sweat, NPSH.
Net positive suction head.
What is it, and why is it destroying equipment?
NPSH is the single most critical parameter in pump installation. It is a measure of the liquid state right at the inlet of the pump. Specifically, it is the difference between the absolute static pressure of the liquid and the vapor pressure of that liquid.
Okay, let's break that down for the listener who might be rusty on phase changes.
Yeah.
Vapor pressure is the pressure at which a liquid wants to boil at a given temperature, right?
Yes. We usually think of boiling as something that happens when you add heat, like putting a pot of water on a stove. But you can also boil a liquid at room temperature just by dropping the ambient pressure low enough.
And that relates to NPSH how?
There are two values you have to track. NPSH available, which is dictated entirely by your piping system's layout.
Like how high the supply tank is, the friction in the suction pipe.
Exactly. And then there's NPSH required, which is dictated by the pump manufacturer based on the internal aerodynamics of their impeller. The absolute rule of pumping is NPSH available must always be higher than NPSH required.
What happens if I design a bad system and NPSH available drops below what the pump requires?
The liquid physically boils at the inlet of the pump.
Wow.
Let's go back to our water particle. As it enters the eye of the impeller, before it gets thrown outward, it accelerates to get into the blade channels. Acceleration causes a pressure drop.
Right.
If your NPSH available is too low, that localized pressure drop at the eye falls below the fluid's vapor pressure. Suddenly, the liquid water flashes into vapor bubbles.
And those bubbles are the start of cavitation. I always thought bubbles were harmless. I used to blow bubbles in my milk as a kid. Why are these bubbles destroying steel?
Let's use a milkshake analogy. If you try to suck a highly viscous milkshake through a flimsy paper straw, what happens? You create a massive vacuum, a huge pressure drop, and the straw collapses in on itself.
Right.
Cavitation is similar, but far more violent. The vapor bubbles form at the low-pressure eye, but then the impeller immediately sweeps them outward into the high-pressure volute.
Oh, wow. So they are suddenly surrounded by crushing pressure.
Exactly. The high pressure causes the bubbles to violently collapse or implode. We aren't talking about a gentle pop. These implosions generate microscopic, supersonic shock waves and jets of liquid that slam into the surrounding metal of the impeller.
I've seen photos of this. It literally eats the metal alive. The bronze looks like it has been chewed on by a metallic shark or blasted with a shotgun.
It does. The continuous shock waves cause localized fatigue failure on a microscopic scale, pitting the metal until the blades physically disintegrate.
Oh, that's terrifying.
It destroys the machine, it sounds like gravel is running through the pump, and it drastically reduces your flow. Ensuring your system layout provides enough NPSH available is completely non-negotiable.
Okay, so we've covered the incompressible fluids. Let's shift to the heavy hitters of the gas world. Compressors.
Okay.
These machines are dealing with highly compressible gases, which I imagine completely changes the thermodynamic game.
It changes everything. Because a gas is compressible, pushing it into a smaller volume drastically increases its density and generates a massive amount of heat, which is the heat of compression.
Right.
We have several distinct mechanical architectures to handle this. The most traditional is a reciprocating compressor.
That's the classic piston in a cylinder design, just like a car engine.
Yeah, exactly. A piston pulls air in through a valve, compresses it, and pushes it out. They are fantastic for achieving very high ultimate pressures.
But they have drawbacks.
Major drawbacks. The back and forth motion creates massive, unbalanced shaking forces that
Yeah.
require pouring huge concrete foundations just to bolt the machine down. And crucially, they absolutely cannot tolerate any liquid in the gas stream.
Because liquids are incompressible. If a slug of liquid water gets into that cylinder,
The piston comes up, hits the solid wall of liquid, and the immense mechanical force will blow the cylinder head right off the machine or snap the connecting rod in half. It is a catastrophic failure.
which brings us to the modern workhorses. Rotary screw compressors.
Yes.
I know these use two intermeshing helical rotors, kind of like giant threaded screws spinning against each other. But there are two very distinct types that plants fight over. Dry versus flooded. What is the difference?
In a flooded screw compressor, we intentionally inject a massive amount of oil directly into the compression chamber right alongside the air.
Why on earth would you intentionally contaminate the air you were trying to compress?
Because the oil is doing three critical jobs simultaneously. First, it acts as a mechanical lubricant for the rotors.
Makes sense.
Second, the oil physically fills the microscopic gaps between the intermeshing rotors, creating a fluid seal that prevents the high-pressure air from leaking backwards to the low-pressure inlet.
Oh, clever.
And third, and most importantly, the massive thermal mass of the oil absorbs the extreme heat of compression.
So a flooded screw seals better, runs cooler, and operates quieter. Why would anyone ever buy a dry screw compressor? It sounds objectively worse.
That is a great question. Flooded screws are mechanically amazing, but they have a fatal flaw for certain industries. They leave trace amounts of oil vapor in the compressed air.
Ah, I see.
No matter how many expensive downstream coalescing filters and separators you install, a few parts per million of oil will get through.
Which is bad.
Very bad. If your compressed air is blowing off microchips in a clean room, or powering dental tools, or aerating vats in a food processing plant, you cannot tolerate a single microscopic drop of oil.
So you use a dry screw where no oil is allowed to enter the compression chamber. How does it even work without the oil sealing the gaps?
It requires extreme precision. The two rotors are synchronized by external timing gears enclosed in a separate, sealed oil bath. The rotors themselves never actually touch each other inside the air chamber.
So how do they seal?
Because there is no oil to seal the microscopic gaps between them, they have to run at incredibly high rotational speeds to minimize the time the air has to slip backwards.
And without the oil absorbing the heat, I imagine they run incredibly hot.
They do, which is why they usually require multiple stages with massive intercoolers between them, but they deliver purely oil-free air.
Okay, that makes sense.
Furthermore, they are essential for massive volumetric flows. And surprisingly, because a dry screw doesn't have the delicate flapper valves of a reciprocating piston, the open geometry of the screws can actually tolerate a moderate amount of liquid injection or condensation without destroying itself.
Speaking of liquid injection, that brings up a really unique, almost bizarre machine, the liquid ring compressor. When I read the source material on this, I had to read it twice.
It is one of the most fascinating fluid dynamics designs in engineering. A liquid ring compressor actually uses a captive ring of water or another specific liquid acting as the mechanical piston.
Walk me through how you turn a puddle of water into a piston.
You have a vaned rotor mounted eccentrically, meaning off-center, inside a circular metal casing. Before you start it, you partially fill the casing with water.
Okay.
When the rotor spins up, the centrifugal force throws the water to the outside wall of the casing, forming a spinning, solid ring of liquid against the wall.
Okay, I am picturing a hollow ring of water spinning, but how does that compress air?
Because the rotor is mounted off-center. As the rotor spins, the blades are dipping into that water ring.
Right.
On the inlet side, the eccentric geometry means the inner surface of the water ring is pulling away from the rotor hub, creating an expanding void between the blades that sucks air in.
Oh, wow.
As the rotor continues to spin to the discharge side, the geometry forces the water ring closer to the hub, shrinking the void and compressing the trapped air.
The water ring is literally acting as a flexible, liquid piston face, expanding and contracting the volume between the metal blades. That is genius.
Yes. And because the compression is happening against a yielding wall of water, the machine is completely immune to liquid slugs entering the inlet. In fact, it welcomes them.
It welcomes them.
Yeah, the liquid ring actively scrubs the incoming air, trapping dust, corrosive fumes, and particulates down to the micron size. It is incredibly robust and is the undisputed champion for pulling vacuums on dirty, wet chemical processes.
Okay, so we've moved the fluids, we've compressed the gases.
Yeah.
Now, these fluids are hot from compression or cold from expansion,
Yep.
and they need to exchange all that thermal energy with other parts of the process.
Exactly.
This takes us to the massive steel tubes we see all over refineries, heat exchangers.
This is where we bring two fluid streams physically close together without letting them mix so they can transfer their thermal energy across a solid boundary.
Right.
The absolute workhorse of the global process industry is the shell and tube heat exchanger. It is exactly what it sounds like. A bundle of small tubes placed inside a large, heavy outer pressure pipe called a shell.
One fluid inside, one fluid outside.
Right. One fluid flows inside the tubes, the other fluid flows outside the tubes, trapped within the shell.
And there are incredibly strict mechanical standards for these, right? I kept seeing the acronym TEMA in the notes.
Yes, the Tubular Exchanger Manufacturers Association, or TEMA. Yeah, the E-type is the industry standard. It has a single-pass shell, meaning the fluid enters one end of the shell, flows straight across the tubes, and exits the other end. It's rugged, economical, and handles most jobs perfectly.
So why use anything else?
Because sometimes pushing hundreds of gallons of fluid from one end of a 20-foot shell to the other creates far too much friction.
The pressure drop becomes too high. You are losing the head pressure. Your pumps just work so hard to build. So what do the engineers do?
They step up to a J-type shell. This is a divided flow exchanger.
Divided flow.
The fluid doesn't enter at the end. It enters through a nozzle right in the middle of the shell. Once inside, the flow physically splits in half, with one stream flowing to the left exit and one flowing to the right exit.
Why does splitting the flow help the pressure?
Because pressure drop is a function of both velocity and travel distance. By dividing the flow in half, you halve the velocity. And by entering in the middle, you cut the travel distance in half.
Oh, that's compound savings.
Exactly. The result is exponential. The shell side pressure drop in a J-type shell plummets to about 1/8 of what it would be in an E-type shell handling the same total volume.
That is a massive hydraulic gain just by moving the inlet pipe to the center. And then there is the massive K-type. What is that used for?
The K-type is exclusively used for kettle reboilers and vaporizers. If you are boiling a liquid on the shell side, say turning liquid butane into vapor, you need physical space for the vapor bubbles to separate from the boiling liquid surface.
That makes sense.
A K-type has a heavily oversized outer shell, usually 1.6 to 2.0 times the diameter of the tube bundle itself. It looks like a swollen belly.
Right.
That empty upper space allows the vapor to disengage from the liquid pool and drift to the top exit nozzle without carrying destructive droplets of heavy liquid with it.
Now, inside all of these shells, the tubes aren't just floating freely. They're supported by plates called baffles. But baffles do a lot more than just hold up the metal, don't they?
Their primary thermal function is to direct the shell side fluid. If you didn't have baffles, the fluid would just take the path of least resistance and shoot straight from the inlet to the outlet, ignoring most of the tubes.
And we don't want that.
No. Baffles force the fluid to flow in a zigzag pattern, constantly crossing back and forth over the tube bundle.
Which increases the fluid's velocity and creates turbulence.
Exactly, and turbulence is the key to heat transfer. Fluid naturally wants to form a stagnant, insulating boundary layer right against the metal tube.
Like a blanket.
Yes. The turbulence generated by the baffles violently rips that boundary layer away, continuously bringing fresh fluid into contact with the metal. That dramatically increases the heat transfer coefficient.
But there's always a thermodynamic trade-off. We know this by now.
Always. Tighter baffle spacing means higher velocity, more turbulence, and better heat transfer. But forcing the fluid to turn all those corners costs you significantly more pressure drop. And crucially, it introduces the danger of mechanical failure.
Let's talk about the pain points and misconceptions here, because heat exchangers seem to be where plant operators suffer the most chronic, agonizing issues.
That's very true.
The first one is a concept we can call the fouling factor trap.
Fouling is the enemy of thermal efficiency. It is the deposit of solid insulating material onto the heat transfer surface.
Like what?
It could be hard mineral scale from hard water, rust, and corrosion products, or even biological growth like algae in a cooling tower. It acts like a blanket, choking the heat transfer. So when an engineer initially designs an exchanger on their computer, they mathematically add a fouling factor.
which is essentially a calculated safety margin. They
Yes.
assume the tube will get dirty, so they build the exchanger 20% larger than theoretically necessary so it can continue to hit the required temperatures even when coated in grime.
Exactly. It makes logical sense on paper. You want a safety net.
But here is the vicious trap.
Yes. Engineers are naturally conservative. They treat this fouling factor as a catch-all safety margin for all their design uncertainties. They oversize the exchanger massively just to be safe.
Right.
But think about the fluid dynamics. What happens when you push a fixed flow rate of water through a heat exchanger that is way too large?
The fluid has too much room. The cross-sectional area is huge, so the velocity drops drastically.
Yes. And low velocity is the primary physical catalyst for fouling.
Oh, I see where this is going.
When the velocity drops, the turbulence drops. The fluid no longer has the kinetic energy to physically scour the tube surfaces. Microscopic sediment and particulate matter that would have been kept in suspension and carried away by a fast-moving stream suddenly slow down, drop out of the fluid, and bake onto the hot tubes.
That is wild. Adding a massive safety margin for dirt actually causes the dirt to accumulate faster.
Exactly.
That's like buying running shoes 3 sizes too big to prevent blisters and wondering why you keep tripping and hurting yourself.
It is exactly like that. By trying to be overly conservative and specifying massive bloated fouling factors, engineers literally guarantee that the machine will foul and fail faster than if they had designed it tightly.
So what's the better way?
The modern, enlightened approach is to design for high velocities. You want the heat exchanger to be self-cleaning, utilizing the kinetic energy of the fluid to scrub itself, rather than just building it oversized and waiting for it to inevitably choke to death.
And the second major pain point with heat exchangers is structural, tube vibration.
Yes. Flow-induced vibration. This is the dark side of high velocity. As we push the fluid faster to improve heat transfer and prevent that fouling, the fluid slamming across the tubes in crossflow creates aerodynamic shedding.
Shedding.
It is the same physics that makes a flag flap in the wind. If the fluid shedding hits the natural resonant frequency of the metal tubes, they begin to vibrate violently against the steel baffles.
I've heard stories of this. Operators say the heat exchanger literally starts humming or screaming.
It sounds like a jet engine, and the vibration will literally saw through the thin metal tubes at the baffle intersections in a matter of hours, causing catastrophic leaks where the shell fluid mixes with the tube fluid.
If an operator hears their brand new heat exchanger screaming, what is the fix? Do they have to rip the whole unit out?
Not necessarily, but the fix requires mechanical ingenuity. The vibration happens because the unsupported length of the tube, the distance spanning between the baffles, is too long, making the tube too flexible.
So just add more baffles.
But if the designer just adds more standard baffles to support the tube, the pressure drop will skyrocket and the pumps will stall.
Oh, right. So how do you support the tube without blocking the flow?
You change the baffle geometry entirely. One solution is the no tube and window design.
What's that?
You literally remove the tubes from the outer edges of the bundle where the fluid turns the fastest, eliminating the crossflow impact on the most vulnerable tubes.
Clever.
An even better solution is a rod baffle system. Instead of solid metal plates, a rod baffle uses a matrix of thin steel rods to hold every single tube firmly in place on all 4 sides.
Oh, nice.
It locks the tubes down rigidly, but because the rods are thin, it allows the fluid to flow longitudinally, parallel to the tubes, completely eliminating the cross-flow vibration while maintaining an incredibly low pressure drop.
It is brilliant how structural mechanical design solves what is fundamentally a fluid dynamics problem.
Yeah.
But, we are talking about baffles and tubes and shells. Before any of these heat exchangers, pumps, or compressors can be bolted onto a concrete pad, they have to actually be manufactured.
Absolutely.
That takes us from the theoretical to the extremely physical. Let's look at the gritty reality of machining and tooling.
I'm glad we are covering this because we can design the most perfect thermodynamic fluid system on a supercomputer. But if the metal components aren't machined correctly down to the thousandth of an inch, the entire plant is compromised.
Yeah.
The factory floor where these alloy shafts are cut, ground, and formed is where our theoretical math meets brutal reality.
Let's look at the tooling first. Machining a massive stainless steel shaft for a megawatt compressor or drilling thousands of holes in a thick steel tube sheet involves immense friction and mechanical forces. The cutting tools themselves take an absolute beating.
They do, and a good machinist is like a forensic scientist. Inspecting the wear pattern on a cutting tool tells you exactly what is going wrong in the thermodynamic process of the cut.
Give us an example.
For instance, Flank wear, where the side of the tungsten carbide cutting tool smoothly rubs away, is usually an indication that the cutting speed is simply too high, generating too much friction, or the tool grade isn't wear-resistant enough for the alloy being cut.
Flank wear sounds like normal degradation.
Yeah.
But thermal cracking is a completely different beast, right?
Yes. Thermal cracking is a catastrophic tool failure. It appears as tiny, jagged cracks running perpendicular to the cutting edge.
Does it just get too hot?
It doesn't come from the tool just getting too hot. It comes from violent, rapid temperature variations. Thermal shock.
How does that happen?
Imagine doing intermittent machining. Let's say you are cutting a shaft that has a wide keyway slot milled into it.
Okay.
The cutting tool is slicing through solid metal, heating up to white-hot temperatures due to friction. Then, it hits the empty gap of the keyway.
Ah.
It spins in the cool air for a fraction of a second, rapidly cooling down, then it slams back into the solid metal. That rapid cycle of expansion and contraction shatters the carbide edge.
Makes total sense.
Or it can be caused by a sloppy operator whose liquid coolant supply is sputtering, splashing cold liquid onto a white-hot tool, and then stopping.
That ruins the tool and destroys the surface finish of the part. But an even more dangerous operation on the factory floor is the grinding process. I teased this in the intro.
You did. Grinding wheels are essentially artificial rotating rocks. They are composed of abrasive grains held together by chemical binders,
Right.
and they spin at terrifying speeds, often over 10,000 RPM. The centrifugal forces trying to rip the molecular bonds of that wheel apart are massive.
It's a lot of energy.
If a grinding wheel has internal damage and fails while spinning, it doesn't just crack. It explodes into heavy, jagged shrapnel. It is a highly lethal hazard that has killed many machinists.
And how do we prevent that? How do you know if a heavy, solid wheel has a microscopic crack hidden deep inside it? Do you use x-rays?
No, the safety protocol is actually beautifully simple and relies on acoustic physics. It is called the ring test.
The ring test. How does it work?
Before mounting any new grinding wheel, you suspend it freely by passing a pin through its center hole. Then, using a non-metallic implement, usually the wooden handle of a screwdriver is standard, you gently tap the side of the wheel at a specific angle.
What exactly are you listening for?
You are listening for a clear, resonant, metallic ringing sound. Because the wheel is a solid, homogeneous mass, the acoustic sound waves travel cleanly and continuously through the material, reverberating.
But if there's a crack?
If there is a hidden microscopic crack anywhere inside that wheel, the physical gap of the crack disrupts the propagation of the sound waves. Instead of a ring, you will hear a dead, flat thud.
And if it thuds?
If it thuds, you take a hammer, completely smash the wheel to pieces, and throw it in the dumpster so no one else can ever accidentally mount it.
That is such a simple analog test, protecting lives in a highly advanced manufacturing environment. But the danger of grinding isn't just to the operator. A bad grinding process can silently destroy the metallurgical integrity of the part being made.
Absolutely. This is a major hidden pain point. Abrasive cutoff, or incorrect wheel dressing.
What does that mean?
As the wheel cuts metal, the abrasive grains are supposed to fracture and fall away, exposing sharp new grains. But if the operator uses the wrong wheel or pushes too hard trying to remove stock rapidly to meet a quota, the wheel glazes over.
So it stops cutting.
It stops cutting and starts aggressively rubbing. This generates extreme, localized, searing heat on the surface of the metal part.
It scorches the metal.
It does far more than just leave a discolored burn mark. That intense, localized heat can actually alter the crystal structure of the steel. It can temper and soften hardened steel, ruining its wear resistance.
Oh, wow.
Even worse, if the hot metal is suddenly quenched by a splash of cutting coolant, it can cause local, brittle rehardening. This rapid metallurgical phase change induces immense internal stress, creating microscopic surface cracks that are invisible to the naked eye.
Let's trace the butterfly effect of that mistake into the real world. Imagine a microscopic thermal crack forms because an operator pushed too hard with a dull grinding wheel during the manufacture of a pump shaft.
Okay.
That beautiful polished shaft gets shipped to the plant and installed in one of those massive centrifugal pumps we talked about earlier. It runs smoothly for 6 months.
Right.
But it's experiencing cyclical rotational stress millions of times a day.
Yeah.
Maybe the system experiences a slight NPSH drop, causing a tiny bit of cavitation vibration.
But very realistic scenario.
The stress focuses entirely on that microscopic grinding crack.
Right.
The crack propagates, it grows a fraction of a millimeter every week, and then suddenly you have a massive fatigue failure. The heavy steel shaft snaps cleanly in half at 3,600 RPM.
Ooh.
The pump internals destroy themselves, the fluid flow stops, and an entire chemical process has to shut down, costing an absolute fortune. All because a factory worker used a glazed grinding wheel.
That is the ultimate lesson of this entire deep dive. Everything in mechanical engineering is deeply, intrinsically interconnected. The metallurgy dictates the machining limits, the machining dictates the mechanical integrity, and the mechanical integrity dictates whether the thermodynamic system survives. You cannot design a plant on paper without understanding the steel.
Speaking of metallurgy, let's talk about one more machining danger that absolutely terrified me when reading the notes. Machining magnesium.
Oh, yeah. Magnesium is an incredible engineering material. It is incredibly lightweight, very strong, and dampens vibration well. It's used heavily in aerospace,
Right.
but it is highly reactive chemically. When you machine a block of magnesium on a lathe or a mill, you are cutting away fine metallic chicks and dust. The surface area of the metal is massive.
Right.
If an uneducated operator uses a standard water-based cutting fluid on those hot magnesium chips, a violent chemical reaction occurs.
Wait, water makes it react.
The magnesium oxidizes so rapidly that it actually strips the oxygen molecules directly out of the water, releasing pure, highly explosive hydrogen gas.
You are literally manufacturing a hydrogen bomb on a factory lathe.
Exactly. And the cutting tool is generating sparks. The fire danger is extreme. A magnesium fire burns blindingly hot and cannot be put out with water because water just fuels it.
So what do you do?
When machining magnesium, you must absolutely avoid water. You have to use specific low-acid mineral seal oils or lard oils to lubricate the cut, which safely smothers the chips and prevents oxygen from reaching the hot metal.
Okay, so our metal parts are machined safely. The microscopic cracks were avoided. Our pumps are moving the fluids without cavitating. Our heat exchangers are properly sized so they are self-cleaning and aren't vibrating to pieces.
Everything is running.
The plant is finally running. Now we reach the capstone of plant management, energy auditing and optimization. The system works, but how do we stop this incredibly complex beast from bleeding money?
Enter the energy audit. This is where we step back from the microcomponents and look at the macro-level metabolism of the entire facility.
Where do we start?
The fundamental philosophy to any professional energy audit is incredibly strict. You always start with low-cost conservation measures before you even glance at capital-intensive equipment upgrades.
Walk me through the low-hanging fruit.
It starts with the most obvious mundane systems. Lighting. You walk the plant floor. Are high bay lights burning in unoccupied storage warehouses?
Probably.
More subtly, look at the fixtures themselves. The accumulation of airborne industrial dirt and oil on lighting fixtures massively drops their lumen output. A plant manager might think they need to spend a fortune on new LED arrays, when really they just need a janitorial schedule to wipe off the reflectors.
Just clean them.
Exactly. And when fluorescent or high-intensity lamps start to age, their electrical efficiency plummets long before they actually die. A smart auditor will recommend group relamping, which is systematically replacing all the bulbs in a zone at once rather than waiting for them to burn out individually and paying an electrician for expensive ad hoc spot replacements.
What about the process cooling? HVAC and chilled water consume massive amounts of power.
Adjusting chilled water temperatures is a classic zero-cost win.
How so?
Let's say a massive mechanical chiller is supplying water to the plant at 42 degrees Fahrenheit. But if you look at the actual heat exchangers on the floor, the chemical process only truly needs 46-degree water to function perfectly.
Oh, I see.
The auditor will tell the operator to adjust the thermostat set point up by 4 degrees. Raising the chilled water temperature slightly increases the suction pressure on the refrigeration compressor.
Meaning less work for the compressor.
This massively decreases the amount of thermodynamic work the compressor has to do. It significantly increases the chiller's efficiency, and it costs absolutely nothing but a few keystrokes on a control panel.
Okay, once you've wiped the dust off the lights and tweaked the thermostats, where do you spend the big money?
That's when you look at hardware upgrades. Air conditioner economizers are a phenomenal investment.
What do they do?
If the outside atmospheric air is cooler than the return air inside your building, the economizer physically opens massive mechanical dampers and uses the free outside air to cool the process, completely shutting down the energy-hungry mechanical compressor.
Free cooling.
Exactly. Heat recovery units are another. We talked earlier about flooded screw compressors generating massive amounts of heat.
Right.
Instead of dumping that heat into the atmosphere through a cooling tower, you can install a heat recovery unit to capture that waste heat from the compressor oil coolers and use it to preheat your boiler feed water or your domestic hot water.
Right.
You are harvesting exergy that was going to be thrown away.
Let's talk about the silent killers of plant efficiency. The major pain points that auditors find hiding in every single facility. I'm talking about air leaks and steam traps.
They are the absolute bane of industrial efficiency. Let's look at compressed air first. Operators treat compressed air like it's free because it's just air. In reality, it is one of the most expensive utilities in a plant because of the massive exergy destruction required to mechanically compress it. A tiny hole in a rusted air pipe, just 3/8 of an inch wide, at 100 psi doesn't seem like a big deal. It just hisses quietly in the background.
But it adds up.
But that single tiny leak will bleed over 6.6 million cubic feet of compressed air in a single month.
Wow. And the compressor in the basement is just running nonstop, burning massive amounts of electricity just to feed that single leak.
Exactly. And steam traps are arguably worse.
What exactly is a steam trap?
A steam trap is a mechanical valve placed at the low points of a steam piping network. Its entire job is to let condensed liquid water out of the pipe while physically trapping the live high-energy steam inside so it can continue to do work.
And what happens when they break?
The internal mechanisms wear out, and they almost always fail in the open position.
Oh.
When a trap fails open, live high-pressure steam blows straight through the valve, bypasses the heat exchangers entirely, and vents directly into the condensate return line or out to the atmosphere.
You're just throwing energy away.
You are literally taking the expensive natural gas you burned in the boiler and venting its thermal energy directly into the sky. A regular, routine ultrasonic surveillance program where a technician listens to the high-frequency hiss of the traps to find the broken ones pays for itself almost immediately.
Now, there's a big misconception in corporate management that you could just buy your way out of bad maintenance habits. I hear executives say, let's just buy a massive multi-million-dollar centralized energy management system, an EMS, and let the computer run the plant perfectly.
Yes, the technological silver bullet myth. A centralized EMS is a powerful data tool. It can monitor thousands of data points, control valves, and track trends. But an EMS is just software.
Right.
It often just duplicates what simple time clocks, local thermostats, and manual switches can do perfectly well.
So it's not a substitute for human competence.
Not at all. If the baseline maintenance culture of the plant is bad, if floor operators are constantly putting controllers in manual override, if steam traps are ignored for years, if air filters are so clogged they collapse, a massive EMS will just give you a very accurate, high-definition digital record of your plant running terribly.
This brings up a point I want to emphasize. If you are listening to this and you are tasked with auditing a facility, what stands out to me about the whole audit process is the human element.
Definitely.
An auditor can't just walk in, read the nameplates on the machines, drop a heavy binder of thermodynamic calculations on the plant manager's desk, and leave. You have to talk to the operators. You have to treat the maintenance personnel with genuine respect. They are the ones who know which valve is always stuck. They know why the pump sounds weird on Tuesdays. They know why that bypass line was open 3 years ago and never closed.
They know the secrets of the plant.
If you ignore the maintenance culture, your brilliant thermodynamic efficiencies will never actually be implemented.
I couldn't agree more. The operators are the central nervous system of the plant. An audit only works if it empowers the people actually turning the wrenches.
Speaking of the people turning the wrenches, let's close out this masterclass by helping them directly. We scoured the internet, dug into the forums, and pulled the most popular, hair-pulling questions that plant engineers are asking online right now about these specific systems.
Sounds fun.
Let's do some rapid-fire troubleshooting, but I really want to know the why behind the fixes.
I'm ready. Let's dive into the physics.
Question 1. Why is my air-cooled condenser suddenly experiencing backflow in the tubes? Vapor is supposed to go in the top header, and liquid is supposed to drain out the bottom, but some of the tubes are flowing backwards and trapping non-condensable gases, choking the system.
This is a classic maddening flow maldistribution issue.
How does that happen?
In a massive air-cooled heat exchanger, you have a giant fan blowing ambient air upward across a huge bank of finned metal tubes. The hot vapor is inside the tubes. The cold ambient air hits the bottom row of tubes first.
Makes sense.
Because the air is freshest and coldest at the bottom, the temperature driving force on that bottom row is massive. By the time that air flows up and reaches the top row of tubes, the air has already been heated up significantly by the lower tubes.
So the temperature difference at the top is much smaller. The bottom tubes are condensing the vapor into liquid way faster than the top tubes.
Exactly. And here is where the fluid dynamics bite you. Because the bottom tubes condense everything so rapidly, the pressure drops heavily inside those specific tubes.
Okay, I see.
The vapor in the top tubes hasn't fully condensed yet, so it reaches the exit header at a higher pressure. Fluid always seeks the lowest pressure.
Oh,
So the vapor from the top tubes actually gets sucked backward up into the bottom tubes from the exit header to fill that low-pressure void.
and when it flows backward, it traps air and non-condensable gases in the middle of the tube, creating a dead zone.
Yeah.
How on earth do you fix a thermodynamic imbalance like that?
You actually have to intentionally hobble the bottom tubes.
Hobble them.
Yeah. When manufacturing the bundle, you design it with fewer fins per inch on the bottom rows. By removing fins, you reduce the surface area, which decreases the heat transfer efficiency of the bottom tubes, bringing them into balance with the top tubes.
That is so counterintuitive.
It is. Or, if the unit is already built, the operational fix is to install a small backup condenser on the exit header to continuously bleed off the excess vapor, ensuring a positive forward pressure gradient in all the tubes.
Incredible. You have to literally make the bottom less efficient to force the whole system to work together. Okay, question 2. My vertical thermosiphon reboiler is surging violently. It chugs, the flow stops and starts, and it shakes the piping. Did I undersize the heat exchanger? Is it too small?
That is a terrifying situation to stand next to, but the diagnosis is usually the exact opposite of what they think. The exchanger isn't too small. The instability is coming from low system pressure combined with high heat flux. In a thermosiphon, there is no pump. The boiling liquid creates a density difference. The vapor is lighter than the liquid. That drives the circulation naturally.
So what causes the violent shaking?
If the heat flux is too high, the liquid flashes into vapor too violently inside the tubes. When a liquid turns to vapor, it expands massively.
Right.
The rapid acceleration of that expanding vapor creates immense back pressure. We call it vapor acceleration loss. If that back pressure spike momentarily exceeds the natural hydrostatic driving head of the liquid column feeding the exchanger, the flow stalls.
The vapor expansion literally pushes the incoming liquid backward out the inlet.
Yes. It blows the liquid back out.
Right.
With no liquid, the boiling stops, the pressure drops. Then, a massive slug of cold liquid rushes back in, hits the hot tubes, and violently flashes again.
Ouch.
It's a massive, destructive surging cycle called two-phase flow instability.
So how do you stop the surging? If the pipe is choking, my instinct would be to make the feed pipe bigger to let more liquid in.
Which would actually make it worse by reducing the friction.
Wait, really?
The counterintuitive fix is to add a restriction. You physically install a throttling valve or an orifice plate in the liquid feed line leading to the exchanger.
Wait, the system is struggling to flow, and your solution is to choke the pipe with a valve. How does adding resistance stabilize the boiling?
It's about changing the system curve intersection. By adding fixed frictional resistance, you dampen the pressure fluctuation.
Okay.
The pressure drop is forced to occur across the physical valve rather than randomly inside the boiling tubes. This hydraulically decouples the steady upstream liquid supply from the chaotic downstream flashing, forcing the system to find a steady-state equilibrium flow rate rather than violently overcorrecting.
That is brilliant. You use friction to enforce order. Final question. Question 3. How do I choose between a centrifugal pump and a positive displacement pump when my required flow and pressure land right on the border of their performance curves? I could theoretically use either machine for the exact same numbers.
When the hydraulic numbers overlap perfectly, you have to stop looking at the pump curve and start looking at the fluid properties and the system constraints.
Okay, what's the primary factor?
Viscosity. If the fluid is highly viscous, like pancake syrup, heavy fuel oil, or polymers, a centrifugal pump will be a disaster. The impeller will just churn the thick fluid, generating massive heat and losing all hydraulic efficiency.
So what do you use?
For high viscosity, you absolutely must go with a positive displacement or PD pump, like a gear pump or a rotary lobe pump, which physically traps and scoops the fluid forward regardless of thickness.
What if viscosity isn't an issue? What if it's just clean water?
If it's water, but you have a process requirement that needs strict, precise chemical metering, meaning you need exactly 1 gallon per minute, regardless of downstream pressure changes, a PD pump is still the answer because it delivers a fixed volume every rotation.
Oh, I see.
But if you don't need exact metering and the fluid isn't viscous, the centrifugal pump is your undisputed champion.
Hmm.
Centrifugals are vastly simpler mechanically, they have wider safe operating margins, they deliver smooth flow without pulsation, and they are significantly cheaper to maintain over a 20-year plant lifespan.
It always comes down to knowing the nuance of your specific system. Which brings us to the end of our deep dive. My friend, we've covered thermodynamics, machining, system design, and auditing. Leave us with a final thought to mull over.
We've talked extensively today about entropy generation minimization. We talked about calculating the exact theoretical limits of a system, reducing the bloated fouling factors, and increasing fluid velocities to make heat exchangers perfectly self-cleaning.
Right.
We are constantly chasing peak thermodynamic efficiency. And as artificial intelligence begins to take over the thermal design of these massive industrial plants, the AI will run these fluid models flawlessly.
I'm sure it will.
It will inevitably remove the human safety factors and the fouling margins because the strict mathematics dictate that those margins are wasteful and inefficient.
Yeah, that makes sense.
But I wonder, will our systems become so perfectly optimized, so tightly matched to the absolute theoretical limit of physics that they lose their mechanical robustness?
Oh, wow.
If an AI designs a heat exchanger with zero excess margin, what happens the day a slightly off-spec batch of gaseous fuel causes unexpected soot in the boiler? What happens when a microscopic flaw in a grinding wheel slightly changes a centrifugal pump's vibration profile, altering the flow by 2%? Are we designing out our safety nets in the blind pursuit of thermodynamic perfection?
That is a haunting thought. A perfectly optimized plan might actually be the most fragile plan of all. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.